Hello, hello, hello. Oh, still more people. Okay. Okay, we'll start a second.
Yeah.
Okay. Hello, hello. We are going to start. I'm just every time trying to put this. Okay, okay. Um, okay, we're. Okay, okay. Okay, feels so good. All right. So I assume I'm thinking people can see and hear me, and I'm thinking so. Can someone confirm you can hear me, right?
Yes, we hear you.
Great, thank you very much. It's like, isn't that, some people find this a really boring part of class, but I find it so gratifying. It's like a question that we can all get right without a doubt. Yeah, all right, so you can hear me. You can see me. You can see the board, I think, in a second. I'm trying to have the board take up less space. We're gonna, all right, so here's where we are logistically. We're gonna do logistics first and make sure there's no questions about logistics. I believe that at 5 p.m. today, maybe that's a slightly approximate, but basically we're going to end class at 4 like we're supposed to. And of course, I'm always like a minute or two late. Oh, wait a second. Even as I'm saying this, I am so sorry. Even as I'm reviewing these logistics for you all, something has just occurred to me. Don't half of you have lab right after this class? Could someone confirm that? I know half of
Yes.
you have lab before. Yes, wait a second. It's amazing that no one's brought this up yet. So that means when this class is over, half of you, for all we know, can be free. I mean, maybe half of you go to jobs and lives and children and so forth, but half of you go to something other than physics, and the other half of you are stuck in lab right after this. If that's true, right? I mean, you just confirmed it, right? Yes. I can't, this is how polite a group you are that no one's even brought this to my attention. So that means, and I was just about to confirm the logistics that we all agreed yesterday. Like, I don't want to change them anymore. I don't want to confuse people anymore. But it's occurred to me just as I'm reviewing them that if I'm not mistaken, that means half of you could start working on this test right away after class, and the other half of you could not. And that is not what I intended. Again, I apologize. This is occurring to me as I'm saying it. So maybe someone stop me if I'm off on a weird path, or maybe Professor Wu's already addressed this. Someone's in there. Maybe Professor. I'm gonna look in the chat, but they all have morning. Oh, that's interesting. Well, that's a very fair thing to say. Okay, that's a very gutsy, fair. I mean, gutsy meaning that maybe other students would be upset that someone just said that. That's a good point. They have all morning and you don't. Okay, that's true. All right, look, if lab is until 6:45. Well, look, all right. I'm going to continue saying what I was just about to say. I'm just going to review the logistics because this group has never, we haven't had an exam together before. And I was going to take quick questions to make sure. Now, I'm going to keep reviewing the way I was. I'm going to take it that you've all thought this through and you're not too worried about it. And by the way, I'm not saying you should be worried. You do have plenty of time to take the test. It's just something it's just an imbalance I hadn't thought of. But so if it's really, although there's another lab session tomorrow afternoon. Huh. That's another good point too. All right. I can't believe how rational you people are. It's like, why are you not running and I don't mean that about whoever is running the country, but why this group is not running the country is yet to be shown to me. But okay, I'm going to keep reviewing exactly what we said yesterday. In the back of my mind, I'm going to ruminate over the possible implications of this half of you having lab and not, and I'm going to take it very seriously how mature you're all being. But I'm also going to take seriously like what Gabrielle just said, right? Which Eddie just, I'm going to take seriously what Gabby said. But for the moment, let me just review where we were so there's no confusion. What I think we all agreed was that at about 5 p.m., I would post an exam. I would post it in Google Classroom, which means you receive it through Google Classroom, and I think that means you're notified of it by email. At this point, it will look like a regular assignment in Google Classroom in that it'll have a place for you to deposit your final product, and you get a grade on it and all that. That will be posted at that, according to plan, would be posted at 5 p.m. Then you would have till midnight, which really means 11:59. So the clock doesn't, so the day doesn't change. You'd have till midnight on Friday of this week. And I would program that into Google. So in the case of this test, so you would have from 5 today till midnight Friday to do anything and everything necessary or desired for you to understand inside and out every bit of this, the questions in the document, so that by Friday on separate pieces of paper, like just like homework, and this is kind of why we practice the homework so many times in a way, just do this the same way on separate blank pieces of paper. You'll you'll write out all your solutions to the exam as thoroughly, as neatly, as sort of personally as you can. Like you'll explain everything as much as you can. So really, you'd like use it as an opportunity to prove that you really get whatever it is you get. And strategically, that means you'll over explain things that you're really confident of. And of course, you'll be thinner on things you're not. But you will write out your whole document on separate pieces of paper. That means if you want, you can retype the questions and give yourself more space. Do whatever you want, but you'll on every separate piece of paper, as though it were a blue book, you'll make it 100% clear what question you're answering, where your work is and what your answer is. Ideally, so that's what you would hand in by midnight, and then it would get graded, and you'll get well, I should say this, you'll get a raw score on it. That will be the first thing that's returned. That is an exam score for sure. Like obviously exams matter more than homework or something. But what you'll get back is a raw score, and then I don't usually curve raw scores, but there may be extra credit or something like that we'll talk about. And as you'll remember, how that score will then go into your average. I mean, it will be averaged with the other test score and the lab stuff, and then all your homework and everything would be piled on top of that in a manner that will produce many of the effects of a curve. I'm saying all this in advance so that so that when you get a raw score back, if for some reason, if it's 65, does that mean you failed the exam and I'm sorry, say it's a 55. Does that mean you failed the exam and failed the course and like everything is no, no, and no? I mean, maybe you might end up failing, but it doesn't mean any of that. If you got a 55, really, or something, the first thing you'll want to know is what was the mean. If it turns out that the mean on this test was a 45 and you got a 55, I'm telling you right now, because of the way the whole grading system works, you should understand if the mean on the test was a 45 and you got a 55, that means you did significantly better than the mean. That means you're at least already, for all intents and purposes, like that's a B minus or something, or a C, like a B minus, if you're trying to do that scorecard in your head while the semester progresses. Like, I just want to be clear before you even take this test that you should not translate your raw score into your final doom number or something. In effect, if you like, the whole course is curved by the homework so that numbers do not translate like that. Somebody will get an A in this class is another way of putting it. Someone else will get an F, but okay. What else about the logistics? Oh, again, hopefully it'll be made clear in the test. The test will have an equation sheet in it that you can use, but it's also the case that you'll use whatever resources you want. You'll talk to friends if you want. You will know that I know that that's happening, and you should not judge yourself harshly for getting whatever help you want to navigate through this test. Go on the web. But then again, know that in the final analysis, whatever you write down, you are in effect claiming to actually understand. Like, If you want to take it to the extreme, I reserve the right to like do an oral exam to anybody if I really think that they just wrote a bunch of symbols that are garbage to them. You should be prepared that I could ask you questions to defend what you're writing and you'd be able to answer them. I mean, do I ever do that? Like almost no, but that's so that's like the logistics of it. It also means probably in the last section of this class, if I get to what I want to, of today's lecture, hopefully I will put you in breakout rooms and have you help each other for one last sort of opportunity on the material with like, and trade phone numbers and stuff, or whatever people trade at this point. Because I'm telling you, you cannot believe how much I actually wish people would work together on physics and how hard it is to get people to work together as much as would be necessary, except when they're in the same room. So at the end of this, I am going to give you an opportunity to work together, to also to leave the feeling that like when you leave here, I'm telling you it's going to be logistics that make it harder for you to collaborate on this exam than it is morality. Okay, I'm trying again. So if you have more questions about substance and stuff by the end of this class, that might be addressed in the break rooms. I'm not going to do a lot of substance today because I'm afraid I'll get bogged down and spend 3 hours again on old material. I don't mean again, but there's one last thing to say about this, and then we'll. I will tell you. I mean, well, what else? Yeah. So we're going to get. So in a minute, I'm going to ask you if you have logistical, like expectation questions, rules questions, stuff like that to make sure we're all clear. But then barring that, most of what I'm going to discuss in class today is going to be moving on with the material and trying to coordinate with your lab responsibilities. Most of what I say you're not being directly tested on. I know that's confusing. Most of what I say today is not on this exam, but it's connected enough that hopefully it will help you still understand better today. Like I don't want to put people in a conflict situation, but I don't think we have time to keep explicitly going over the exam much more. So we're going to move on with new material. The ideal of today is that what at least I'll prepare you for, if I'm distracting you for the exam, is to help you with your is to give you what you need to write your next lab report for WU. So quick question on that before I get your questions. What lab are you up to with, or what is your next lab assignment obligation to WU? Like, is it a formal report or a post lab or what? Could someone tell me?
The next closest thing, post lab 3 is due tonight. And the next thing is formal 3, which is due, I believe, either Friday or Sunday. But right now in class, awesome. we are doing lab 4.
Perfect. Okay, that is thank you for that perfect answer. And for proving that you were paying attention. Okay, that's totally helpful. So what? And I even caught that little Friday Sunday thing. So I've been a little bit less in touch lately with you than I should. But I got right. We don't mean to have you have an exam and a lab report due both on the same day. So, and I don't want to change any more, confuse people. So if you guys are trying to persuade him to give an extension till Sunday, I think that's totally fair, and I would put in a vote for that too, for what it's worth. But the good news is that everything I'm going to do today in class, anything that seems like it's not directly on your exam, is absolutely about lab 3 and 4. What I want to talk about today in class is absolutely about lab 3 and 4, which sounds like is what you're up to and that what's due. So hopefully, this will not be a waste of anybody's time, or blah blah blah. Okay. Wait, so in the last, when we have about 45 minutes left, or even an hour, if someone wants to remind me, like, can we shift gears and go back to the exam now? Please do. Like when we have 45 minutes or so left, I will shift gears, meaning I'll make sure that any questions still haven't been, any questions about expectations are addressed. And at that time, if you will have been working, we will have been talking, you can private chat each other, whatever. By that time, I will have assimilated more what not Gabby, what Hawks. Wait, don't tell me. I know. Wait, this is my first test. This is my first test. Think of it in a minute. It's Hawk. It's Hawk. Where did it go? Wait, sorry. This is Gabrielle. Right. What Gabrielle said about the 2 labs thing. I'm having that in the back of my mind as we have class today. You can too. You can send each other private chats and stuff. And And what that would, and if enough people tell me in our last hour, again, I worry about too many changes because it freaks people out when there's too many changes on stressful things. But due to the lab thing, I forgot, I certainly would be happy to consider like posting your exam right at the end of lab. So like sort of everybody, gets it at the exact same moment, and everybody's free to work on the same moment. I would, in other words, like that's like an hour and a half change from what we said. I would certainly consider that. You guys can talk about it in the thing, but I don't want to make it a big focus right now. So what all that means is that my bank is calling. What all that means is that momentarily I'm going to shift to directly talking about the material of lab 3 and 4. We are in lab 4. Great, great, great. Yes, this is very helpful. Thank you. I'm going to shift to that material, but first I want to address, I don't want to address big physics questions now, but anything about the exam that's sort of concrete that I can say, like about rules, or even if it's just like how did you get, no, yeah, anything concrete that I can answer now, I would love to before we get too rolling. Or like, someone saying, I've heard about these YouTube things, but the links aren't working, or anything like that about the class management questions. I'll give you a second. Okay. All right. And you can keep asking. Like, I'm going to start. I know once I start talking, I just get carried away. But if you think of a question about the exam and want to interrupt, that is, politely, I may not be able to answer it at that moment, but please feel free. I don't want to leave confusion hanging. All right, but if that's the case, yes, I'm going to start. Actually, wait, can I get an electronic thumbs up of just like, yeah, it's okay to start rolling now and just start dealing with the physics of lab 3 and 4. Oh, cool, that was fast. Wow, all right, I'll take it. Great, wow, fabulous. Okay, then that is what I will do. Okay. So lab 3 and lab 4, what they do is okay. Okay. What's exciting to me, and it really is about lab 3 and 4 about this material, is we've been sitting hard on harmonic oscillation, thinking about it hard, trying to unpack what it means for a system to act like a mass on a Hooke's law spring. Everything we've been saying so far, everything that's on the exam about harmonic oscillation applies to particles. Like a thingy thing can harmonically oscillate back and forth. I mean, so can abstract numerical variables like the strength of a force. Oh, you question? No, okay. Variable numerical values can fluctuate and oscillate as well. But the key thing is that particles are capable of being in a place and time, and then being in another place and time, and then another, and doing so to make this pattern, this cosine thing that we've been talking about. Now, why we care so much is it turns out that if you take a whole collection of harmonic oscillators and you organize them in a certain way, or nature organizes them in a certain way, then what you can build, both physically and what we can build conceptually in our mind, looking at it, is not just oscillation of a thing, but propagation of an unthingy thing. Like the key about, of course, I mean, you've been there in the lab, but well, I don't even know what that means that you've been. Actually, I should ask you. You haven't been in the lab. You've been in like virtual weirdo lab, but in principle, you know that you've been talking about like wave pulses in lab 3 and 4. And now we're into the real meat of the course. I mean, 3 weeks in, we're into like the exciting area of physics, because now we're talking about the motion of not a particle or a thing, but of a pulse. And a pulse is not an object. It is not a discrete or identifiable or countable or distinguishable thing that you could say here it is and here it isn't, or I got the whole thing in my hand or I don't. No, a pulse is nothing like that. A pulse is an abstraction. It's like I'm going to be more specific about what it is, but whatever you've been watching go across a string, whether in simulations or in fake lab or whatever, or when you go to the ocean and you watch ripples in the water and you call them waves, which is what we're now going to start talking about, right? The first thing to understand is you're not watching anything actual at all. You're watching a system or a behavior or a phenomenon. But in fact, let me be really specific here. What I'm really saying is, okay, this is a mouthful, but this is what I'm saying. In English, we're going to start talking about waves now. You've already started talking about them in lab, or specifically, I should say, we're going to start talking about wave motion, or the motion of wave pulses. Fundamentally, what a wave is a kind of motion. That's first and foremost. Wave modifies motion. Wave, there's no such thing as a wave thing. There's no type of thing called a wave. There is a type of motion called wave motion. And what it consists of in English is a situation in which there is measurably and predictably some trip that is observed from some location A to some location B. Like if we can track, chart, observe, perceive, quantify some kind of journey of something that goes from A to B, but if at the same time we can be confident that there's not a single object in the world, not a single particle, not a single identifiable, discrete, countable, separatable piece of mass in the world that necessarily went from location A to B. If we can measure and predict a motion from A to B for which there is no discrete mover that actually travels all the way from A to B, then that's what we mean by wave motion. And that is a pretty heavy thing. Like I'm trying always in physics to say stuff that I kind of know if you think about it, but you may not have thought about that way. And I'm also trying to say, since it's a physics class, that when I say a thing like this, I mean it universally and literally. I don't mean this as a metaphor. So I'm saying, like, if you stand at the beach and waves are coming in, right? You're like, oh, the wave is coming in. Oh, watch out, there comes the wave or whatever. First of all, what you really mean is here comes the wave ripple or a particular wave crest or a wave pulse. Like waves is the whole phenomenon that's going on in the whole ocean or whatever that you're looking at. But anyway, if you're like, oh, there's wave ripples coming in, there's wave ripples coming in. Oh, watch out, the next one will be here in a second, right? All of which are reasonable things to say, because you literally could have a stopwatch and a ruler and watch the ripples go, and you could time like, oh, that ripple's going like 2 meters per second, so get out of here because it's only 2 meters away. I think we all kind of know somewhere in the back of our minds that partly what's exciting about that ripple that you track and come in toward you, if you're, at Coney Island or the nice one, Rockaways or something, is that there's no water molecule that is traveling in toward you at 2 meters per second. If you see a ripple coming from the south toward you while you're standing in the north and it's coming to your head and it hits your head, I think you understand, but I need to make clear, all that's moving is water for sure, but there's no water that actually did the thing that you just observed. No water molecule was coming like horizontally toward your face, as I think or as lab 3 and 4 are trying to demonstrate, trying to demonstrate. And what I'm trying to say in English now is there's water molecules that are like going up and down and up and down and up and down, like some going up and down over here and more over here going up and down and more over here going up and down. And somehow the whole rhythm of the whole thing creates something that comes in, which from here on in, I'm going to call a pulse, right? Whatever it is that's traveling in observably, I'm going to call a pulse because I want to drum in the fact that there is no actual thing there doing that. You could say energy is traveling. You could say a crest or a trough is traveling. What is really a pulse? Ultimately, the purpose of this course, what I really think a pulse is a little bit a pulse. I mean, in England, what I mean by it is like that little hump in the water that you're tracking with your eye. But what it is a bit, well, not literally a bit, but a pulse is a bit of information. What's traveling when waves travel is, I would say, information. Now, it does depend how you define information. There are certainly some people that would not agree with this use of the term, including my best friend from 7th grade. But what does he know? A lot. So if you don't like the word information, you can say energy or something like that. But first, I just want to say that what's interesting about what is worth studying about waves is that wave motions are a type of motion that do not require a mover. Hold on a second. So, as such. Oh yeah, that's a great question about. Oh, sorry. Okay, just got a good question. I will try to adjust it to everybody. Oh, cool. Wait, these are good questions. Okay, wait. So, I'm gonna try to answer. I'm looking at the questions, but some of them are private, so I'm trying to be. Okay. Let me try to say this one more time. For some people, when I dive into the math, which I will in a minute, for some people, of course, the math will actually make this more concrete. For other people, the math will make it weirder. So let me try just one more time to say what I'm saying. Let me give a different example, in fact, to all the private questions that I just got, which are good, but bear with me. I think I'm going to try to answer them. When I say water waves, okay, water waves happen in the water for sure. And water is a thing. Water is H2O for sure. Like water is made up of lots of little water molecules. Now, if anything is moving in the water at all that you're watching, I fully am saying, and I do agree with anybody who's wondering, I absolutely think that when you're at the ocean and you're watching waves, the only thing you could say that's moving is water molecules. I mean, there's fish and stuff, but for sure, water molecules are moving when you watch waves move. What I'm trying to say, and I'll use a different example in a second, what I'm trying to say is the motion that you observe with your eyes macroscopically is the result of a bunch of water molecules moving. But if you looked microscopically, you could never find, or there's no reason to expect to find any individual water molecule that's actually doing the motion that you're macroscopically observing. Every individual water molecule is certainly moving, but not in the way that you see. So, like if you see the water come in, like travels, if you see a big hump, a crest, travel toward the sand from south to north, and then like break and crash on the sand. Like, of course, all of what you're seeing is water doing stuff, yes. But there's no individual molecule that went from south all the way to north. A better example that might make this more clear, and yes, you can have high tide and low tide and things like that. For sure, the waves sometimes crash up high on the sand and sometimes low, because waves can be bigger and smaller for various factors that we'll get into. But perhaps this example will make it better. And also, I also have a movie on this, but a different example I'm trying to say maybe is sound. If you believe that sound is real and sound exists, and I do, like if you can hear me right now, if you believe, and whenever I say if you believe, I don't mean that sarcastically, but I just do mean the more you get into physics, the more you end up questioning everything. And I don't know where your assumptions begin and end, but sound, I'm shouting now, presumably from my mouth, like someone's hearing. This is another good question. Okay, the questions are coming fast, and these are good questions too. I'm not actually saying that everything is a wave. Okay, so here's what I'm saying. Like, I can throw a baseball to you guys. I can throw a baseball to one of you guys. And that's one type of motion. That's called particle motion. And that type of motion, if I say I throw a baseball, what it means is and if we say I throw a baseball 3 meters and we time it with a stopwatch, so like it took 4 seconds, All of that means the following, that there was a baseball that was in my hand at the beginning of the journey at one moment. Then we started our stopwatch, and with our eyes, we could track this one object called a baseball, which is different from everything that's not that baseball, right? Like I could hold the baseball in my hand, say, that's my baseball. Then it starts traveling to you. So what one moment it's really near me, and then the next moment it's a little farther from me, and then the next moment the baseball's a little farther. And we could track, like we could take photographs or what do you call it, stop action photography or something. And and by the time the baseball gets to you and everybody says, oh, the baseball traveled 3 meters and it took 4 seconds, what we all implicitly mean by that is that there was some object that is over there now that was over here before, and that in fact traversed all the intervening points between here and there. That's what it means for a particle to move. And in that sense, I don't think a baseball is a wave at all. Like, I'm not, I know quantum mechanically, my mother, like weird, but I'm not trying to say anything weird yet, actually. A baseball is a particle, it's not a wave. The motion of a baseball is particle motion. The thing goes from me to you. That's what we see, and that's what happens. But take sound in contrast. When I talk and the sound goes from my mouth to your ears, I don't know if you've thought about this before or not, but no, but when we say sound goes from my mouth to your ears, we don't mean to imply that if we had a big enough microscope or telescope or something, we could find any bit of anything in the world called like a sound particle or something that actually went from my mouth and then ended up in your ear. Like there's no object in the world that we think did that or had to do that in order for sound to get to your ear. Like that would be gross, first of all. But second of all, I mean, more specifically, even if you happen to be aware, like, oh yeah, right. I know what I'm saying. There's no such thing as a sound particle, but he's just being weird because like what there obviously is air. And when Yavrab talks, he's like, his tongue is moving the air, or in my vocal blah blah blah. I'm vibrating the air, and then like air is vibrating and doing stuff and going from his mouth to your ear. Like, well, now the air, what I'm saying is air to sound is like water to water waves. It's true that to say sound travels through air means air molecules are moving in some kind of a very cool, productive way. But it's not to say that there's any air, there's no air molecule that's going from my mouth to your ears for you to hear. I mean, even if we were in the same room, that would be me spitting on it. That's not how sound works. What sound does is there's air molecules over here that are vibrating back, that are harmonically oscillating back and forth within a small neighborhood. And next to them, there's air molecules harmonically oscillating back and forth or up and down or something within a small neighborhood. And so each little air molecule is taking a little turn to vibrate. And it's that that rhythm or what's being passed from me to you. And I really just start getting to the math, so you'll see it. But what's being passed from me to you involves nothing but air if I talk in the same room as you. But there's no air molecule that has to go from me to you in order for the whole thing to work. I don't know if that analogy makes it more concrete or less. And again, we're going to get into this more directly. But the last thing I can say, so I'm trying to post these videos of the lectures, and I'll hopefully you can see. I'm throwing a bunch of stuff onto YouTube. All on the same channel, most of which is like very, very long, and no one would ever want to watch unless they need it. But one of the things I threw up recently, I'll write in the text, was called VOI Part 1. That if you're interested, if what I'm saying seems at all like it might be clarifying something to you, but it's not quite there yet, I did sort of break all this down in a long PowerPoint presentation I did a long time ago that's called VOI, i.e. the velocity of information. It's ultimately about the speed of light and ultimately about Einstein and relativity, which may make it more exciting to some of you, or you may not care. But the beginnings are trying to break down exactly what I'm saying here. If you want to look at it at your leisure, I'm probably saying too much in English, probably should get to the math. But what I'm really, really trying to say is that wave motion is different from particle motion. I know what made me think of the film. The wave motion is like, this may help some of you. What I'm saying is if you ever look at like a diner or a theater marquee, like in Times Square or something, I don't know if we're all still New Yorkers in this class or what's going on. Some of us are from Venus or something now, but if you look at a theater marquee or a diner, and it has that one of those signs around it with lights that go around. Like there's a bunch of bulbs around. I could. This is the beginning of the slide, so I could probably pull this up in a second. This image, but if you picture like an Eat at Joe's Diner kind of sign, and there's a bunch of light bulbs going around it, and you, huh? That's interesting. Okay, I'm looking at the chat. If you picture a bunch of bulbs around a sign, and if you've ever had that experience where you see like the light going around the bulbs, right? It's sort of hard to say, but you see like, oh, it's like a red light or a neon light or something. It's like going around and around the sign. And it's a cool effect, like light going around the sign, or around the letters of the sign. But if you go up to the sign and look closely, of course, what you find is there's a bunch of bulbs all just sitting there, and one bulb goes on and then it goes off, and then the bulb next to it goes on and then it goes off, and then the bulb next to it goes on and then it goes off. And if it's done fast enough and smoothly enough, and you could do this on computers and stuff, but it's like fun. If it's done fast and smoothly enough, then what it looks like from far away is like like someone holding a light bulb is like running around the sign, like that there's a light moving around. But that's not what's happening. There's a bunch of lights that each one of which is going on, off in place. In other words, you could measure how long it takes for the light to make a full trip around that sign. You can measure it, you can make predictions. It's totally legitimate motion. The light is undergoing a trajectory around that sign, but there's no light actually doing that. There's a bunch of individual lights doing individual things that together create the phenomenon. That's what I really mean by a wave in English, or in rough English. That's what I'm trying to say now. It may be helping. If it's still not landing right, like bear with me and let it sink in for a second, because I'm just going to make it worse, I think. So I'm going to start trying to show you what I mean by this mathematically. But this is the stuff of physics that we can actually like study motions that don't as such, or that have movers in a different way from particle motions. So how does this come about? How do we get from harmonic oscillation to wave motion? Well, that's where all the phase constant business comes in. Okay. How to build a wave motion from a bunch of harmonic oscillations. Oh, and from now on, the word I'm going to use for wave motion is propagation. Whenever I'm talking about, in other words, physics only cares about motion. If the thing that's moving is actually a thing, we call it motion. If the thing that's moving is not a thing, if it's an unthinking thing, like a wave pulse, we then refer to its motion as propagation, just to remind ourselves that what's happening is different. And when waves move, ultimately we talk about wave pulses propagating from one place to another. Now, my claim is that a wave pulse can be made up from, can be composed from, physically and mathematically, conceptually, from a bunch of oscillators if we're careful. How? This is how. Okay. Okay, we're going to consider one harmonic oscillator, i.e. like one little mass on a little spring, on a Hooke's law spring, that is configured so as to oscillate along the y-axis, which really means we're going to let this thing oscillate, and whatever axis it's oscillating along, we're going to call the y-axis. Okay, and no tricks, no friction, no weirdness. So say we have this one oscillator. Let's just set it kind of like in lab 1. And it's, it'll be set up. It's set up by itself, so we necessarily know that it will, if we let it go, excuse me, from some initial position y naught, then we know it's going to oscillate freely at a constant angular frequency, which is the square root of its spring stiffness over its mass. I'm going to call its whatever its initial displacement from equilibrium to be y naught. Why not? Because not. And this is one oscillator. Since this is one oscillator, there's no reason not to just start my stopwatch the minute this thing is at maximum maximum displacement from equilibrium, i.e. We're going to hold this thing from rest at some initial position. That initial position will not be position. Oh, that's just, then it's all just like homework number one, lab number one, thing on a screen. The most we can say about all this, we would say this. You have this coming out of your ears at this point, but this is like review for the exam. If we have one oscillator, then we know, we know this is true. And we know the solution to it. Now we've been saying, we know, I can go back to the page if you want, but I think that's all you have to, you know. We know if there's one oscillator, then its equation of motion could be written like this, right? I'm going to leave the zero in for a reason. Like I'm saying the phase constant phi is zero, but I'm going to write it as zero because I want to contrast it with other phis in a moment. But here we have our one oscillator, looks like this. Oh, yes, I'm sorry, yes?
On the other page, what was that in front of a zero? Is that an F or plus?
Sorry, on the other page, this page, the page before. Wait. Sorry, this, am I on the right page or go back one more page?
No, you're on the correct line where it says y naught equals y zero. What is that, a plus or F?
Oh, sorry. That's supposed to be a does not equal. So I'm saying here, so I'm saying by definition, yeah. I'm saying by definition, y naught is the position y at t equals zero, but I want to just remind everybody that that is not the same thing as saying that it equals zero. Like we're not going to start this thing at the equilibrium position. We're going to start it anywhere else but there. Does that make sense?
Yes.
That's all right, cool. Very good question. All right. So now, and as to why this is coming up again, in a way, I'm trying to, well, we're transitioning, we're building, well, everybody will see why this is coming up again. This is a brief review of simple harmonic oscillation, but now I'm going to move on with the material. There's a reason we did it in the first place. We're going to move on and say, okay, wait a second now. Sorry, and let's even be really clear. Yeah, in fact, I'm going to take this one step further. I'm going to say, no, it's fine. It's fine. Okay, we have this later. What I'm going to do now is remember, I made this big point of the phi constant, the phase constant. At first, we didn't care about it at all. We just had zero sitting there. Then we realized, oh, there could be a phase constant. So we have to be careful. Like sometimes it's zero, but it doesn't have to be zero. But we still want to make it zero whenever we can. And I made this big deal of saying that you can make it zero whenever you only have one oscillator. But if you have more than one, that's where you have to worry about the phase constant. And that's exactly the situation I want to look at now. I want to say, imagine we've set up this one oscillator vertically, but next to it, somewhere nearby it on a different axis, on say the x-axis, we put another identical oscillator. So let's say now consider adding another identical oscillator, but displaced from the first one, like nearby it, but not at it, displaced some amount x, i.e. nearby on a different axis. So we now have, I just did that, well, so it says, okay. So I'm saying now consider adding another identical oscillator, but one that's displaced along the x-axis somewhat. So in other words, we're now going to have this. We're going to have another one over here. Same K, okay, same M. But before you even go to drawing, let's go a step further and say it's going to be displaced along the x-axis. And let's also, although they're both going to be identical oscillators, let's put them out of phase with each other on purpose. Let's also start the new oscillator out of phase with the first one. So everything else will be identical, and they're both vertical oscillators, but they're both going to be placed on the x-axis. And the difference between the two, for example, is that we could call the first one, let's say that the next oscillator starts pi/4 behind the first one, pi/4 radians, or in other words, an eighth of a cycle behind the first one. I'm saying pi/4 arbitrarily. It could be pi/2, it could be pi/3, it could be anything. I'm on purpose making it pi/4 because it's an easy number to work with, but I don't want you to think that it has to be a very special number like pi/2. It doesn't. I'm just saying, let's say we separate the two by phase constant, so that in other words, whenever the first one is in the equilibrium position, the second one is not. It's somewhere else besides the equilibrium position. And then when the second one gets the equilibrium position, the first one is somewhere else, somewhere specifically, somewhere else in the cycle. All right, so we're going to separate them by a certain amount in the cycle. No big deal. I'm just saying, let's do that, right? But you might see where this is going. The next thing, so we have two oscillators that are identical, but they're out of phase with each other, kind of like two windshield wipers on a bus, maybe, or something. And they're both. But now I want to take it a step further. Let's say we introduce a third and a fourth and a fifth. Let's make a whole bunch of oscillators and lie them all along the x-axis, make them all identical, make them all vertical oscillators, but they're all along the x-axis. And let's say that each one of them is separated by a certain amount in phase from the one next to it. And because we always like to keep things as simple as possible at first, let's just say that they're each separated. They're all separated. They're all out of phase with each other, but let's say all by the same amount relative to one another. In other words, what if we do something like this? So we have like, let's stretch out a whole bunch of oscillators, make them each identical in every respect. Initial amplitude, spring stiffness, mass, all vertical, but let's stagger them in phase. Let's stagger them in phase, but in a steady way. So this is kind of like, let's change something's velocity, but let's maintain constant acceleration. We're going to introduce our first change here, but we're going to make the change as unchangey as possible. What I'm really trying to do right here is create the simplest possible meaningful collection of oscillators that I can. That is, I could take a whole bunch of oscillators, knowing everything you guys now know about oscillators. What we could do is take 100 vertical oscillators and lay them out horizontally on the lab table. Like 100 vertical oscillators, we could all lay them out next to each other in a horizontal alignment on the table, and then we could let them all oscillate. The simplest possible thing would be to let them all oscillate in phase with one another. But if we did that, it would all look like this, like a whole 100 oscillators would go up, and then 100 would go down, and 100 would go up. That would be the simplest, truly the simplest possible thing we could do with a collection. But it's so simple, it's stupid. It's so simple, it's not meaningful, because then really all we've done is made one big oscillator. There's no sense in which that's a collection. It's just a really wide thing that's going up and down. What I'm trying to do here is take a collection of oscillators and use the multiplicity of it to some kind of advantage. I'm trying to actually take advantage of the fact that I happen to have 100 springs sitting around, or 1,000, and I'm going to put them all into a collective oscillator, but I'm going to make them all out of phase with each other so that they're actually doing something distinguishable. But that's already so complicated sounding. I want to keep it as simple as possible at first. So I'm going to say that all these oscillators are staggered in phase, but staggered in a constant way. Mathematically speaking, what I'm saying is this. So I'm saying, let's take a whole bunch of oscillators. Again, one individual oscillator is the nature of your exam. That's what you're being tested on. Now moving on with the material and saying, this is not on the test, but this is what you're dealing with in lab 3 and 4, is now that we know what oscillators do, let's take a whole bunch of them. Let's set them all up and let's make them all identical in all respects, except that the first one, the first one's going to start at a maximum displacement from equilibrium, or in other words, as soon as it gets to that point, we're going to start our stopwatch and start paying attention. At that very moment, I'm going to say, assume that at that very moment, I believe the next one won't be right there at the same place in the cycle. It won't be at the beginning of the cycle, so to speak. It'll be behind by, oh, not a half a period, because that would be pi. And if it were pi, so it would be, if it were pi, if this number were pi, then they'd be like this, going like that. Right, but I'm saying not that dramatic. Let's say the second one is delayed by about not a half a period, which would be pi, not a quarter of a period, which would be pi over 2, but like an eighth of a period, which would be pi over 4. Let's say that, and then let's say the next one is delayed by pi over 4 relative to its neighbor. So the second is staggered by pi over 4 from the first. The third is staggered by pi over 4 from the second. The fourth is staggered by pi over 4 from the third, et cetera, right? But all these phase constants, to be mathematically consistent, they're all being measured. They're all being measured from the first, from the first. Each one of these individually is measured relative to 0, right? No, that's supposed to say measured relative to 0. So if I went and put a whole bunch of oscillators like this down, I would get some kind of interesting motion, I think. I'd get, well, maybe like the water fountains at the Brooklyn Museum of Art, maybe, or something, or like a bunch of windshield wipers doing something interesting. But I would still only be able to understand this whole collection of oscillators with a collection of equations, like I just wrote down. But if I look at the equations and think about what's happening, if I set it up like this, again, this is the simplest meaningful use of a collection of oscillators. They're staggered in phase, but in a constant way. Consider the phase, contemplate the phase. Okay, if we think of n, lowercase n, as an index, as a counter, so the very first oscillator, we'll call it the 0th oscillator, that's the oscillator of n equals 0. The very next oscillator we'll call the first oscillator, that's n equals 1. The next oscillator is the second oscillator, et cetera, right? So if we just think about what phi is doing as a function of n, right? We're setting this up on purpose. I hope you see that if we graphed phi as a function of n, it's a straight line, right? If you want to know exactly what your phi is, how far delayed you are from 0, well, the second oscillator is delayed by 2 fourths, 2 pi over 4. The third oscillator, if you just look back here, the first oscillator is not, the 0th oscillator is not delayed at all. The first oscillator is delayed by 1 pi over 4. The second oscillator is delayed by 2 pi over 4, et cetera, right? So but if I name an oscillator, you could immediately name to me what its phase delay is relative to the beginning of the line. And if we graph them, we get a straight line like this, right? Fine. So what? Well, let's take it just one step further then. Instead of just saying that the phase delay that we give to an oscillator is a function of the numberth oscillator it is, like that's kind of right now what I'm saying is if it's a third oscillator, it's going to get a phase delay of 3 pi over 4. And if it's the seventh oscillator, it'll get 7 pi over 4. But I don't, what does that mean in space and time? Seventh oscillator, third oscillator. Why don't I say this? Let X sorry. Yeah, let X equals some simple function of n. That is, let's just be really concrete and say, you know what, we're going to let's make sure, even though you might have already been assuming we were doing this, in order to keep this whole model as straightforward and dealable as possible, let's make sure that we line up these oscillators along the x-axis. We actually space them evenly, right? So let's space the oscillators evenly along the x-axis. So meaning that the 0th oscillator is at the edge of the meter stick, and then let's put the first oscillator a centimeter away, let's say, or a meter away, and then put the second oscillator 2 meters away from the edge. Put the third oscillator 3 meters away from the edge. So let's imagine that now what we have is a whole bunch of oscillators that are evenly spaced on the x-axis and which are identical in every way, but for which their phase delays are in direct proportion to where they are in the x-axis. That's what, then in other words, we would be saying that if we graph phi as a function of x, a much more meaningful thing to do, if instead of just graphing phi as a function of the oscillator index number, which is kind of very specific to a lab, I mean, it's very, sorry. Well, that's supposed to be a phi. I don't know why I can't draw it. This is a phi, and this is now, instead of n, make this x over here. Instead of just counting oscillators, we're actually plotting phi as a function of position on some x-axis of actual space. Oh, and after I just said that, I just didn't. So this is supposed to be x. Then we would still get a straight line, right? As long as we space the oscillators evenly. And as long as phi was a straight line function of oscillator index, then by spacing them evenly, now phi is a linear function of the spacing. Phi is, right? This is a straight line. Phi x, like the oscillator at the 3rd meter is going to be delayed by 3 pi over 4. The oscillator at the 7th meter will have a delay of 7 pi over 4, etc. So we have the straight line. Well, the slope of this line, right? However you want to think about slope, the slope of this line is clearly constant. So I'm going to give a name to that constant. You're going to hate this. I hate this too. I'm going to give a name to this constant. Unfortunately, the name that is usually given to this constant, which we do need and you'll recognize from lab, is K. And that's really annoying because it's not the same K that we've been dealing with, nor is it the other K that we've been dealing with, nor is it some other K that comes up again later in physics. I apologize on behalf of the whole community. There's a lot of Ks. So this is supposed to be a K. I'm going to draw it slightly differently. I always draw it like this. I'm going to draw it kind of more like a kappa, like I'll put serifs on it or whatever. Let K stand for the slope of this line, delta phi, the change in phi over the change in x, right? In other words, phi 2 minus phi 1. Anywhere you pick on this line, the rise over the run should be the same because it's a line. If we call that slope K, right, then K whatever it is it stands for the relationship between where you are in the cycle versus where you are on the line of oscillators. K is the idea that if you're 4 meters out, that according to this whole picture, you're going to have a delay that's 4 times as great in the cycle, a cycle delay, as something that's all the way at the edge, as an oscillator that's at the edge of this collection. Wait, this is all for lab 3 and 4. Everything I'm talking about here, you'll see when I'm done, hopefully. This is for lab 3 and 4. I'm doing it my way. I'm not doing it in like the order of the questions, of course, because that's like your job. But hopefully when I'm done with this, you'll all see how this relates to both lab 3 and 4. At the moment, it might look like it relates to neither. I'm not sure. You'll see though. What I'm saying though, is according to this whole idea, I'm just trying to put together about, yeah, and I will sum up, just bear with me for a second. I'm getting a lot of, hold on. Right, so the relationship between phi and x I'm saying here is direct proportionality. Phi is phase delay, and I'm saying we're setting up a system of oscillators where you lay them all out on the x-axis, and the farther some oscillator is on the x-axis, the longer you're going to wait till it gets set in motion. Like we start the first oscillator in motion, then we start the next one, then we start the next one, then we start the next one. Oh yeah, phi is a delay as long as what's in the parentheses is a plus sign. If there were a minus sign in the parentheses, I would think it's a head start. Right, so I'm saying delay every time. I'm sorry, I'm saying these in answer to chat questions, but I'm not too concerned. I don't want to confuse anybody, but whether it's a delay or head start, it won't really matter because it's a cycle. But right, I'm assuming it's a delay just because I see a plus sign in the parentheses. So I'm saying, imagine you set up all these springs on the table, all horizontally, and you just like, you flick the first one so it starts going vertically, and you wait a certain amount of time. You wait till it's like almost in the equilibrium position, and then you flick the next one, and then you wait till that one is in the same place as you already decided, like almost the equilibrium position or something, and then you flick the next one, and then you flick. So I'm saying you give a delay to each one that is like the same as the delay that you gave to the last one. So you stagger all of these, and if you're as precise about it as possible, then you're saying that the delay phi is in direct proportion to wherever you're looking in the line. The farther out you get in the line, the bigger the delay is. And by the way, that can go on forever, right? The line can be super long so that you have some oscillator way out here who has a delay of say 20 pi over 4, 20 pi over 4 radians. What does that really mean? That really means 4 pi radians. That means we've gone so far out here that the delay has brought us back to the beginning again. Totally fine. Like these are cyclical processes. We expect that if we wait long enough, we're going to get back to the beginning. So yeah, way down the line, there might be an oscillator that starts at precisely the same time as the one on the edge did. And then the next one after that will start at the same time as the second one did, et cetera. So we're going to get a cycle of cycles. I don't want to get ahead of myself. But mathematically, what I'm saying, here's some for people at the edge of their seat, perhaps very much like the, I'm psyched that Matteo just said, or that someone just said, yeah, Matteo sent an animation. Of course, I'm not going to look at it just yet. I trust his judgment. I'm sure it's a very helpful animation, probably. Maybe I will look at it. But I'll tell you this, the whole goal of Lab 4 is to make animations that exactly show what I'm trying to say. The sense in which I haven't tied it together yet, but I'm totally talking about the underpinnings of Lab 4. You're just trying to make what I'm saying on a computer or with a flip book in Lab 4, unless we've changed the labs. But we're almost there. I really think it will come together. If you, I'm saying now, then if K is the slope, if is defined to be the slope of this function, and this function is describing a situation that we just made up because I'm asking you to consider it. Like I'm saying, let's consider what would happen if we collected oscillators together in this fashion. Well, the bet, I think, I don't know. Then, given all this, then I think what is true is phi itself at any given moment is this K number times X, right? Again, if X is 0, then K is 0. If you're at the edge, you have no delay. If you're a little bit over, if X is 1, then you have 1 times pi over 4 of a radian delay. If you're over 2, you have 2 times pi over 4. In other words, sorry, I'm trying to say I want to say something about the units here. Okay, and the units of K, Olo, I'll stop and ask. According to everything I'm saying now, and again, I'm not making this up. Of course, I'm not making it up, but I am like introducing it. I'm not saying you walked through the forest and you stumbled on this situation, you're trying to analyze it. I'm saying you stumbled on oscillators in the forest, and now you're excited enough by them that you're trying to put them together and analyze or predict what would happen if you did. And the first question I want to ask is, according to everything I'm saying, what would the units of K necessarily be according to all this? Like if phi is in radians and X is in meters, what are the units of this K? Oh, great. I totally see in the chat. Yes, totally. Oh, wow, that was fast. I swear. I like blinked and there was 3 answers in the chat expressed differently, but all right, or some expressed differently. Awesome. Yes. The units of this have to be radians per meter, and it is true that radians are not a strict unit. So you can either say radians per meter, as I will, just to keep reminding us that radians are involved, or you could literally just say meters to the -1, as someone said in the chat, because yes, radians, strictly speaking, cancel out. They don't have to be written in there. So, but K is in these units. K is in this case, in this particular example, K, for example, would be pi over 4 radians per meter, right? K would be. I'm not saying that, in other words, K is the rate at which the number of radians of your phase delay, it's the rate at which the number of radians in your phase delay grows or shrinks depending on how far out you are. So in other words, pi over 4, that original pi over 4 that I introduced as an example, right? I'm not saying all waves have to use pi over 4 in this special way, but if we started, and as someone's there, excuse me, if we started on this page and just decided to separate each a pair of adjacent oscillators by a pi over 4 delay, then what we're saying is for each meter, there's an additional pi over 4 delay. Like each next meter at which you might put an oscillator is another pi over 4 that you're going to have to give to that oscillator for its total delay, right? It's pi over, and we could have done it for pi over 2 or pi over 3 or whatever. But in other words, we could take all right, with all of this talking with, yeah, great question. Okay, I just got a private question that said, is there a name for K? Great question. There is. I'm intentionally not, I'm about to give that name to you. You'll know it when you see it if you haven't guessed it already. Once you see the name, it will bring this a lot together. So I'm not gonna say it just yet, but yes, there is a name for K, and that is a great question, and I'm about to say it. It's like, what I'm saying right now, though, is K, the unnamed piece of notation here, enables us, if we understand it, to capture this whole collection into one equation. A moment ago, I was writing like y equals y naught cosine omega t plus 0 for the first one. Then the next oscillator is y equals y naught cosine omega t plus pi over 4. And then the next one is cosine of omega t plus 2 pi over 4. Well, I could just put that whole package together in one equation and say, maybe it looks familiar. Like because you know, one oscillator is described with omega t plus phi. Now what I'm saying is we can now introduce for the first time a variable fee, so to speak. It's not variable in a weird way. We're just saying, hey, we could take a whole bunch of oscillators and set it up so that each of their fees actually depends on where they are. And we could capture the whole thing by saying, oh yeah, here's our deal. Like we have a whole bunch of oscillators that are oscillating in time, but they're all laid out in space. And each one of them, every single one of them obeys this one equation, because this one equation says that each one of them is going to vibrate in the same way vertically, but just each one of them is going to get a different delay that is going to depend on where it is in the system. So this one equation simultaneously captures all the oscillators. That's the huge benefit. That's the advantage. What's the cost or what's the loss? Well, nothing, except that for the first time in our lives now, in order to do this, the reason the cost is all of a sudden for the first time we have an equation, one function of two independent variables at the same time. We've never, as far as I'm concerned, we've never had to deal with that before in physics or math. Like maybe you have maybe you've taken differential equations or multivariable calculus, but you didn't have to for this class. So as far as I'm concerned, this is a moment in everything I've ever done, if I'm really getting the relationship between math and science up until now, a function is a graph. A graph is from an experiment. An experiment is you tweak one variable and you watch how nature responds with another variable. Like everything in math is independent variable that you play with, dependent variable that responds to it. You put independent variable on x-axis, you put dependent variable on y-axis. You could think of independent variable as kind of like cause and dependent variable kind of like effect. And all the while, if you're doing things right, everything in math and physics up until now has said you put input into that and we'll give you output. And it's one for one. That's why you can put it on a graph, because you have two-dimensional pieces of paper. I'm now saying, as a leap forward for mankind, for a leap forward for electron kind, that we actually can do better than that. We can set up a function that has two inputs, time and space along the x-axis. And what it will return as a value, as an output, is space along the y-axis. And there's many different kinds of equations like this, but the one that we just invented here, if we understand it correctly, captures a whole bunch of oscillators that are lined up along the x-axis, but are all going up and down the y-axis in identical ways, but in ways that are patterned or staggered according to where they are at x. So in other words, for this whole collection of oscillators, if you come along and you see, I have 100 springs on a table and they're all doing this, and you say, hey, that phenomenon, wow, crap is going up and down. That's really exciting. Like I see mass is going up and down on your lab table. Like how high is that thing? If someone said to me, how high is that motion? Like those whatever I'm seeing. If they said, how high is it? That's a fair question, but I would just have to ask back them. I'd say, how high is it? You mean, well, first of all, how high when? Because the thing is going up and down, right? So I would say, tell me when, and then I could tell you, but also I'd have to say, I would not only say, tell me when, well, this is what I mean. What I'm saying right now is what I mean by y equals, I'm saying y is a function now for the first time of two independent variables, x and t. Whenever I write, if I write like y equals, if I do that, it means y is a function of, I think I've been sort of doing that through this class, but now I'm saying here we have a function of x and t, which means if anybody wants to know the answer to the output question, if they're like, what's y? And let me say again, y measures position along the y-axis, x measures position along the x-axis, t measures time on the clock. So if someone walks in and sees all these oscillators doing this stuff, going up and down to various heights, they could say to me, how high is that phenomenon? And I would say to them, well, it's not, that almost sounds like a fair question, but I don't really know how to answer it, because this whole phenomenon is going up and down in time, and it's going up and down like this. So if you tell me, if you want to know how high, you could say to me, how high is the oscillator over here? In other words, you'd have to specify some x position. You could say, how high is this whole phenomenon? How high is this section of the phenomenon going to get at 3 o'clock? You'd have to tell me where you're looking at what time. But if you tell me how far over you're looking and you tell me what time, I'll tell you exactly how high the oscillator at that, like I'll tell you the oscillator at that spot, how high it will be at that time. Height here of any given oscillator depends on which oscillator you're talking about, in other words, how far over, and it depends on time. It's a function of two variables, but it does so exactly according to this function that I've written. And if I write else, I'm almost done. I'm going to take a break. We're almost. I will take questions and stuff in a second. But I'm saying this, which I know you have seen before, and I'm just coming at it from a different way now on purpose. I'm saying if you have this, oh yeah. The answer to the question, what is that K called? Which was a very good question. And I did get it privately, and fair enough. I mean, but good question. What is that K called? It's called the angular wave number. And remember, omega is angular frequency. Oh, hold on. Omega, the units thereof are radians per second. And what omega really meant, we've been saying, is how rapidly something oscillates per time, how many cycles are undergone by an oscillator in time. And that would be a simple oscillator going up and down or side to side or whatever. Well, now I'm saying this K is actually very much like omega. K is in, yeah, well, this is what I'm, right. K is not radians per second, but it's radians per meter. K is how many oscillations or how many cycles you're getting per space. That is, if I did set up all the oscillators the way I'm saying, and I did stagger them in phase the way I'm saying, if you picture what would happen, and I'm presuming that Mateo's animation shows this, I can't like look at it at the moment, and I'll go back to the other page. If you set this all up, you would see things going like I can't do it. You would see things going like this, right? You wouldn't see things going like this. You would see things going like this. In other words, if you set all this collection of staggered oscillators, if you create a collection of evenly staggered oscillators, more specifically, a collection of identical oscillators that are all spaced out that all oscillate along one axis, but are set up, spaced out along a separate axis. And if their oscillation, if their delays or their phase, whatever you want to call it, if where they are in the cycle depends on literally where they are sitting in that line, then you have like this kind of situation. And what everybody knows that as, or observe, or would recognize that as, and call it correctly, is wave. Like I'm saying, if you collect oscillators together and do this tricky thing with their phases, and this is why I care about phase, if you collect identical oscillators and stagger their phases in the simplest possible way, but a way that is still staggering, then what you've created literally is a wave pulse. Like you'll see up, down, like this. And if you watch it with your eyes, you'll see this part is up. Oh, you can't see my hands. Like, okay, so you'll see like this kind of business. And like so when my pinky goes up, right, and then comes down, then my ring finger goes up and then comes down. And then my next one goes up and then comes down, and it ripples through. Well, and so what you see is like you see up over here, but then you see up over here, and then you see up over here. So what it appears to be is like a hump or a crest or a trough moving across the x-axis. But if you think about everything I've just said, there's no object moving across the x-axis. There's a bunch of masses on springs moving continually and very, very specifically, exactly, but all along y-axes. And yet they do it in this alternating way so that what ends up propagating across the line, the x-axis, is a pulse. All that's moving here is metal springs, let's say, but we observe a traveling along the x-axis of the bump, and a bump is not itself a thing. In other words, one last way to put it is, I'm saying every single oscillator had movement that was restricted entirely to the y-axis, but we staggered their phases so that we end up observing motion along the x-axis. That motion I call a pulse. What is a pulse really? Like what? I mean, what are you actually picturing if there's nothing there? What are you seeing move across if there isn't a thing to see? Another way of putting pulse is a disturbance. By pulse, I mean a shape, really. I mean what moves across, what will move across this line of oscillators, what will move through this oscillators is a ripple. What a ripple is a change of shape or a contortion or distortion. If you imagine these oscillators as a long string like lab 3, right? If you imagine a long string stretched along the x-axis, and if you shake one end of the string and send a pulse from one end to the other, as you did in lab 3, and you watch that, and you make a movie of that crest going across from one edge to the other, what you're really watching is a disturbance or a contortion or a distortion, a misshapenness of the string. The string was straight, and then at one moment it was like bent up somewhere, and then it bent down, and then you saw another spot of it be bent up. What you're watching go across is a bend, right? It's not a thing, it's just a shape of a thing. So in other words, a pulse is a disturbance. I'm going to write this on the next page. A pulse equals a disturbance in the shape of some oscillator collection So a pulse is a disturbance in this whole collection. By disturbance, I mean a distortion, a contortion, a perturbation, a deviation from the normal shape, the normal shape of this collection of oscillators. And this collection of oscillators the collection
So then what would be the difference between a ripple and a pulse?
Sorry. Right, very good question. Actually, there's no difference at all. It's just that pulse is like the strict scientific term, and ripple is a little bit more like just to relate to us as human beings. But I use the terms interchangeably, right? I mean, right? Yeah, they're the same. A ripple, a pulse, and so a pulse is like, yeah, they're both the same, and it's whatever you. And good question, and it's whatever you watch with your eyes, so to speak, or whatever you would track if you like in lab 3 when you were tracking how much time it. Well, no, you didn't actually do that. But if you were tracking how much time it takes for some sound wave, let's say, for example, like how much time did it take the sound of my voice to get to your ear, the sound of my voice is some kind of disturbance or ripple in the collection of air molecules. Like we have a bunch of air molecules that are already sitting there between my mouth and your ears. There's a whole bunch of air molecules everywhere, just like there was already a bunch of oscillators sitting on the table before we started this, or there's a whole long string in lab 3. And then what happens is when I talk, some of the air molecules near me start oscillating back and forth. I mean, they could go up and down, like in the whole example. If this were exactly the example I just gave, they would go up and down. Then the ones next to them would go up and down. Then the one next to them would go up and down. And finally, when that up and down motion like got to your ear, I would say the pulse arrived at your ear or the ripple arrived at your ear. And then you would hear my voice. Now, a technical difference between sound and other waves is that actually in sound waves, instead of the molecules going up and down, they actually go in the same axis as X, like they'll go back and forth and back and forth. That's a minor, it doesn't make any difference. They don't hit each other or anything. So by pulse, I mean the same thing as a ripple. And the whole collection of material particles, the whole collection of thingy things that you need to do this, that are themselves oscillating, but then giving rise, they're all oscillating in this specific way and then giving rise to propagation. That collection is what we call the medium. So like air is the medium for a sound wave, string or slinky is the medium for the transverse waves of lab 3. Water is the medium for ocean waves, but you can have a medium without waves, right? You can have water and not have any water waves. You can have waves without water, but then you'd have to have something like air or something else. You can have a thing that's not waving, but you can't have a wave without a bunch of things making it. And those bunch of things is called the medium, are called the medium. I really will take a breath and look at the chats in a second. I just want to make sure we get somewhere with this. So I'm ultimately saying, like, I know you didn't do that. So in lab 3, you just like looked at waves and started breaking them down and analyzing them through a differential equation I'm going to get to. Like in lab 3, you look at this on purpose, look at it from a lab perspective way. So there's no reason you would, so you do that, then here I'm doing lab 3 almost backwards. So there's no reason you would recognize what I'm talking about as being lab 3 until I get to the end. But I'm kind of trying to construct lab 3 backwards here. And in a way, that's where lab 4 comes in, is you're trying to physically build what I'm mathematically trying to say here. Again, if it's still not connected and clear yet to anybody, that's not a shock because I'm not done. And if it were perfectly clear right from the beginning, if I were saying the exact same thing as in lab 3 or 4, that would be a waste of your time because you don't need anybody to say it twice. What everybody needs is just like different ways of looking at something. So, that's a great question. Wait, I'm seeing great questions in the chat. Let me just wrap my thoughts up before they crash at the station. And I'm gonna look at the chat and then we'll take a mental break anyway. What am I trying to say? Oh, I'm trying to say thus. So, the equation of motion for like a freely falling body is like y equals 1/2 at squared plus v naught t or something, right? The equation of motion we decided for a oscillator is like y equals a cosine omega t or x equals whatever, right? Equation of motion means something where we relate time to position in a direct manner. So the equation of motion for a collection, for an SHO collection, according to everything I'm saying here, would be like y equals y naught. And these could be x's too. I'm just defining y to be the axis of oscillation rather than propagation. So this would be the equation of motion for the whole collection. It's now a multivariable equation. I mean, it has 2 dependent variables in it, but okay. This would be the equation of motion for a collection. And what I'm trying to say here, and then I'm going to pause and take questions, is if you really follow what I've just said, I'm arguing that if you can build in your mind or in reality a collection of static oscillations, the equation of motion for that the whole thing would be this, what I just wrote down. And if you step back and look at it, either in reality or in your mind, what you will have just then created is a wave motion, a wave propagation, i.e. this equation that we just wrote down is the equation of motion for wave pulses. It's the exact same equation. Like, I'm basically saying you can build a wave from a collection of staggered oscillators. And in fact, that's the only way. I mean, that is what a wave is. So then, yes, if you differentiate this equation twice, you end up getting what I think, and I think you did this in lab 3, but if you differentiate, so I just got this equation, from analysis. In lab, what you did was you got a y versus t equation from data, and you got a y versus x equation from data, like you charted y versus t, and you charted y versus x from the same phenomenon, from that string that you shook in lab 3 and you videotaped and you put in the computer. Or actually, I don't, wait a minute, I'm assuming, sorry, we're in a virus here. I don't actually know exactly how you did lab 3. You'll have to tell me in a moment. I'm picturing our traditional lab that we traditionally do in the room. So maybe I'm making an assumption here I shouldn't, but I am saying that this is the equation of motion for a wave. And if we differentiate it twice in a couple minutes, we're going to get a differential equation, a second order one that looks a lot like the one we've been dealing with in class, and one that's super important and is not on this exam, it's on the next exam, but that's where we're going with this. I'm momentarily going to differentiate it twice and get a new differential equation. But and so if that's what you're thinking, you're right. Like, that is how this all ties together. But whether you're thinking that or not, I'm not going to do it just yet. I'm going to look at the chat. I'm going to take a breath. We're all going to take a breath. Hold on. And again, you're not be tested on this tomorrow. I apologize if that's confusing, but that's just the way it is sometimes, of course. But hopefully by listening to this, maybe it might retro help you understand some things you're trying to understand for tomorrow. All right, I'm looking at the chat. Radians per meter, yes, absolutely. Is there a name? The name for K is wave number. Yes, wave number, awesome. So you totally saw that. What are you? Oh, just the comma. I'm sorry. That's a great question. When I say that, I apologize. When I say that y equals f of x comma t, that is just notation to mean y is a function of x and also of t. Like the comma, yeah, it sort of makes it look like an ordered pair, but it doesn't mean anything. The comma doesn't really, I mean, yes, it is treating those as coordinates. Like if I had a 3-dimensional piece of graph paper, I'm addressing a chat question that's good about, like, what do I mean when I say this? I mean now that some dependent variable is a function of 2 independent ones, and that means they're both independent of each other. That means if I could actually graph it in 3D, if I had 2 axes down here for me at the base of a cube, forming my 2 independent variables, and then I graphed like the dependent variable up on the height axis, in effect, yes, like ordered pairs, dots, points in this 3-dimensional graph, points would consist of pairs of values x, t, y. Like, I'm saying too much. So yeah, in effect, that is, it's just that they would be ordered triplets, not ordered pairs. So yeah, the comma is kind of doing that. So that's a good question. I don't mean to make the comma too complicated. How can we relate? So how do omega and k relate? That's a good question. Let me go straight. Is that the last? That's a great question. Okay. How do we make? So I am saying now though, the k that I'm talking about now with the fancy serifs on it, that is the K from lab 3 and lab 4. Like, I am talking about wave number now. Like, this is now waves have seeped their way into lecture material. It's not the same K as Hooke's law K. It's not other K, but it is the K from lab. So how do omega and K relate? Great question. Actually, that really does help me move along. I'm ultimately saying this: given if you have this equation, if you have y equals that's my fancy K, which looks like terrible. If you have that, then omega was supposed to be radians per second, right? Angular frequency. One way of putting it, and this is good review for today's exam. Like, here's something just hopefully you'll see if it makes sense to you or not for today's exam. Like, omega was 2 pi over the period. Or I mean, we could also say it was 2 pi f. There's lots of ways you can think about omega, but the convenient way right now is omega is angular frequency. It's like how many cycles you make per second, but where you measure cycles in radians. So each cycle is 2 pi radians rather than just one cycle. Okay, that's what omega was. Well, what's k by that reasoning? If we have some wave, well, Actually, I'll answer the question once. I'm saying K, sorry. In the same way that omega is 2 pi over T, K is 2 pi. It's not radians. Omega was angular frequency, cycles per time. K is wave number. That means cycles per space. Where if you have a wave like this, if you have a graph of the information from some wave like this, then the space between two successive crests is, sorry, I'm being distracted by something. Okay, just like I'll do it one last way. Okay, I'm saying a lot suddenly here. It's a great question. How can we relate omega to K? It's sort of the question, especially if an exam were about any of this, which it will be. It's a great question. So I'm saying, let's back up to lab. We are now talking about waves. In lab, as is appropriate, you sort of see the wave, you make the wave, and then you break it down to its parts mathematically and physically and try to analyze them. Here, in theory, Right, and I totally want to get to this whole vacuum light question. That is actually the ultimate punchline of the whole class. I definitely want to get to it. It's great. Let me try to get to this other thing first, because it's a little bit more pragmatic exam related. But like in lab 3, you created a lab. No, you didn't. You created a wave. And then you broke it into parts. What do I mean by parts? Specifically, what you did was you took the one phenomenon and you, with video, it's again, maybe you didn't do this. I don't even know, but, and I will ask. But in principle, you have two graphs going on in lab 3. One graph of y as a function of t, the other graph y as a function of x. And that's the way it has to be, because nobody has three-dimensional paper, right? So I'm saying that ultimately a wave is actually a phenomenon that intrinsically involves or possibly involves more than one dimension of space, as well as necessarily a dimension of time. So you actually can't graph a whole wave phenomenon at once any more than you can draw a whole wave phenomenon at once. You actually can't. You can take slices and consider them. So you can look at how something is going up and down as a function of time, some little bit of the wave. You can, in other words, hold x constant and look at how y fluctuates as a function of t. That would be looking at one bit, taking like focusing on the movie of your wave, but only watching one little section of it. Or you can look at the whole wave, all x, sorry, or you could hold t constant. That is, take a snapshot of your wave motion, take a snapshot. So you're only looking at one moment in time, but then look at how y fluctuates as a function of x, right? You can't do both simultaneously because you don't have a three-dimensional graph paper. But if you do each one individually, in principle, that's what's going on in lab 3. A wave is a phenomenon for which y as a function of t and y as a function of x are both simultaneously happening and both embracing cosines. They're both going up and down. That's what you're supposed to be seeing in lab 3, that whether you pick one x value and watch as height fluctuates in time, or you pick one time value, one moment, and look at how height fluctuates as a function of distance. But either way, you're going to get a cosine graph. Either way, you get harmonic oscillation. Either way, you don't have a wave. You have you either have a oscillator or you have a picture of a wiggly curve. But what a wave is in effect a bunch of oscillators or a picture of a wiggly curve moving through time. You have to have both to have the whole wave. But the relationship is that omega does to time what k does to space. If you were to graph, the long way of saying, if you were to graph y as a function of x, as I think you did in lab 3, then the x space between any two similar points in the cycle, like the amount of length for a full cycle, the amount of space taken up to get from crest back to crest again is what we call wavelength, as in length of wave. It's measured in meters, and it's usually designated with lambda. So I'm going to say, I'm saying, and I think a lot of people know this from 6th grade or whatever, or trough to trough. Anyway, yeah, trough to trough. Right. If you have a, like, again, what I just drew is a wiggle. That is not a wave, right? That is a wiggle. And one thing going back and forth is not a wave either. This thing rippling back in time, or many of one things, in other words, a wave has to involve time and space. But if this right here is one snapshot of a wave as lab 3, so that it's just one moment in time, and I graph y as a function of x, then we call this distance between any two similar points, we call that the wavelength, or lambda. It's measured in meters, as it should be. I mean, it's a length. And what I'm ultimately saying then, and similar, sorry, just like what we could have plotted was y as a function of time. If we plot height as a function of time, same graph, well, it looks like garbage, same math. But now the interval between any two like points on this graph is what we call the period, not the wavelength, right? Wavelength is on a space graph and period is on a time graph, but they function the same way. They're like the size of the cycle. So just like omega, I can go back to that page in a second. Omega is this, then K, and that is, in other words, radians per second. K is this, which is radians per meter. Omega is 2 pi over the period, 2 pi radians per second. K is 2 pi over the wavelength, 2 pi radians per meter. And in other words, omega is how many cycles you make per, how many cycles are performed per any given unit of time, and K is how many cycles are performed in any given unit of space. They're totally symmetric and parallel. They're functioning the same way, because what a wave is a simple harmonic oscillator in both time and space. What a wave is a bunch of oscillators. Sorry, this is a bunch of things, each of which is harmonically oscillating in time, and all of which we've set to be harmonically staggered in space. Like, that is what a wave is. It's harmonic oscillation in time happening wrapped up in harmonic oscillation in space. It is a pattern of patterns. That's why it's so important to learn the bass pattern first, so harmonic oscillation is like the note, and wave is like the chord or a melody, or some bad analogy. That's like blaming it on owls that I'm bad at analogies. Wait, okay, so wait, I don't know if that, so I can't fully, okay, so to really finish Gabrielle's question, she said, can I relate omega to K? Well, this is the bet. I can relate them conceptually like this. And again, and I can say, like, again, that they're sort of fitting into the whole function in a very similar way. But I can't literally relate them in an equation. I'm not going to tell you that K is related to omega, like if you multiply by 3 or something, because they're not. Like, they're the point is that they're actually independent parameters of each other. They are in, just like omega was based on square root of K over M and came from the materials of the system and was not based on how you configured it. Same thing with K. So these are independent parameters, independent from each other. But they're one's driving time, the other's driving space. It's 302. Yeah, I think that's a good place to play. Well, okay, I still have Gabrielle's other question, or someone's other question. Yeah, wait, let me do one. Yes. Okay, still, yeah, T is here. Yes. So I'm agreeing with all these questions about Gabrielle's questions. I'm agreeing. As far as I know, there's still one question out there that Gabrielle, well, actually, let me answer this and then the next question. There's a short version to the answer and a long. So Gabrielle asked in the chat, oh, sorry, if it was private, I'm sorry. No, it wasn't, okay. And again, let me say, every single one of these questions is great. Occasionally they come in faster than I can deal with, but I don't see why any one of these should be private. I'm not saying they can't be, but nobody should be embarrassed by any of these questions. So, for the collection of oscillators, kx, the term kx only applies to a collection of oscillators, which is, I'm saying, a wave. K will be a constant always, but x varies from, x is a variable. So it's not, this won't be different whether it's a collection of oscillators or a wave. It's the same thing. But to Gabrielle's question of what about like vacuums, very important question to raise the issue of a vacuum, like very important question. Because if you're hearing me at all, I am saying, and this is what's prompting Gabrielle's question, I am absolutely saying that for wave motion to happen, there's got to be some things that are allowed through which it happens. Like I'm saying, wave motion is fundamentally, by definition, a motion that is not ascribed to any one thingy thing or particle. Like when sound goes from my mouth to your ear, there is no bit of air, or there's no like soundtron or something that goes from, and that's not a technological point. Now, I'm not saying we just haven't discovered one yet. No, I'm saying we don't even believe in one. We're not even looking for one. It wouldn't even make sense if we found one. I don't even know what it would be if we found one. For sound to go from my mouth to your ear, we're saying a bunch of air molecules shake back and forth in a very particular way and end up sending like this pulse to your ear. And the implication, one important thing of what I'm saying is air does not, the air is not the sound. Granted, air does not go from my mouth to my ear. On the other hand, if we didn't have the air there, the sound couldn't go from my mouth to your ear, unless we had something else like water or wood or guitar string or something. Like, if you're following what I'm saying, wave motion is a ripple, and the only way you get a ripple is for things to be rippled. Like so why this is science, not Harry Potter or something. No offense if some of my best friends read books or something, but like why this is science is that even though wave motion itself seems very abstract, and it seems like I'm saying crap goes from me to you without there actually being any crap there to do that, I'm at the same time saying I believe in all of this and I can analyze it because it's all, the phenomenon is tethered to actual material objects doing something material and measurable. So I am in effect arguing, I am saying you can shout at me in a room, you can shout at me underwater and something will happen, especially if you're a dolphin or something. You can like shout at me through the wood of a musical instrument or the string, like you can send sound through various types of media. But now directly to Gabrielle's question, according to the logic of what I'm saying, if you literally had a vacuum, like if you didn't have air or stuff somewhere, then sound would not go through. And I will argue that that is true. Like there is not sound in outer space. Outer space may be complicated and have all kinds of like outer space might have radiation or something, which we're going to talk about. But outer space does not have air. Outer space does not have an atmosphere. Outer space is not gases. It's called space because it's supposed to be space, and it is. Like even the moon does not have air or an atmosphere, and people have been on the moon, right? You cannot shout on the moon. I mean, do I know that for a fact? No, but I don't know anything for a fact. Like I don't know, if I'm not dreaming, but to the extent that I know anything and have studied anything in science, and to the extent that anything makes logical sense, in outer space, there is not sound. That's not a myth. You can do other funky things with radio transmitters, blah, which we'll talk about, but you can't like literally shout. If a meteor hits the moon and explode, you won't hear anything. Sound cannot travel through a vacuum, I'm saying, through a true vacuum. Sound cannot. Neither can a water wave or anything else. Now, light, that's a beast of a different mixed metaphor. Like light, it should, if light is a wave, then all the logic I'm saying should also apply. Then you shouldn't be able to have light in a true vacuum. If light is a wave and it's traveling from a star to my eyes, if it is traveling as a wave, then according to everything I'm saying, there's got to be something between a star and my eyes to carry that light, according to what I'm saying. But this is why light is the ultimate nub of the gist. Like, I'm not ignoring this question at all, but in a way, this whole course is designed to get us to the point where we understand light at the end. Light is because it plagued everybody for centuries for exactly this reason. If waves make any sense at all, they cannot go through a vacuum. And if light indeed is a wave, then it can't go through a vacuum. Now, is light a wave? I haven't said that it is in this class. Is there evidence in the world that there is? Yes. Is there also evidence in the world that there isn't? Yes. Has this all been resolved by quantum mechanics? Arguably, sure, yes. But the only way any of the resolutions or any of it makes sense is if you first go through the steps. So I'm not trying to like skip out on this question, but light is precisely understandable only because it is the hardest. It's the end of the line of all these steps. So on the one hand, to understand light, we got to understand the steps first. But on the other hand, of course, there's something being implied by Gabrielle's question, which is great, which is actually what it turns out is light is so excitingly different and weird and wacky. We really can only understand how wacky and weird it is and how it can exist at all if we first understand how to contrast it with all the steps we're doing now. So what I'm ultimately going to say is, can you have light in a vacuum? Yes, you can. And that's how starlight gets to us. But does that mean that light is either not a wave or some very kind of special wave? Yes, it does. And we have to get to that at the end of the course, like when we feel like we understand waves enough to say that. But so I'm not, and I'll hear more from people privately and stuff. I'm not trying, I love that question. We will say more and more about light as the whole course is building toward actually giving a proper non-bullshitty answer to that question. And I apologize for my language, but I can't emphasize enough that the reason I study physics, okay, the reason I started studying physics, the reason I stay in physics, and I'm always excited about it, is precisely because I'm still excited by the wonder of light and how many layers there are to the answer to Gabrielle's question. So I'm giving a brief one now, but really I designed this whole course so that by the time we actually talk about light, we will, I feel like people always were bullshitting about light, and they were, honestly. Like almost everything I've heard about light to this point in science classes is generally out of order and wrong and emphasizes the wrong things. So I'm begging your indulgence to wait a little bit for more answers, but only because it's like the point of the whole course is what is the deal with light. Sound, however, yeah, I'm going to say sound cannot travel through a vacuum. It just can't. And no other wave can, because wave is a wiggle and something has to wiggle for there to be wiggled. Okay, look at the chat. Right. I mean, people say light behaves as a particle and a wave. Now, I'm here to say, I'm not saying that's wrong, but I'm saying I was told that a million times in science classes, and that doesn't, I don't think that, I think that's an obnoxious thing for other people to say to students because it doesn't mean anything. I mean, that's what the whole movie VOI is. If you watch the slideshow of VOI, I try to, velocity of information, I try to address that, but I will, throughout the whole course, I will try to address what does it mean to say that light behaves as a particle and a wave. I know people have heard it a million times, but I really feel like almost every time that's said, it's said in a way that creates more misunderstanding than understanding. So right now, what I'm saying is there is not, in the world, there are particles and particles can move. In the world, there's another type of motion besides particle motion called wave motion, which involves a very complicated behavior of particles. Like, I'm not saying in the world that there's two different things, particles and waves. I'm saying in the world there are things and they move. And then sometimes if you put a bunch of things together, they can move in such a complicated way that it is a way that no one thing can do. So there's two types of motion in the world, particle motion and wave motion. What that really means is there's motion that literally consists of particles, and then there's motion that doesn't. But there isn't, it's not like vanilla and chocolate. It's not like there's particle things in the world and there's wave things in the world. That's what's so deceptive when people talk about light. They get that all. There's not things, there's not waves and particles in the world. There's particles in the world. Sorry, there's not two types of things, particles and waves. There's two types of motion. Particle motion, which means motion of things, and then wave motion, which means motion not of things. Okay, that's all. That's what I'm saying about that for a moment. Let me, you know what I'm going to do right now? I'm going to take a breath. I'm going to put you in breakout rooms so that you can come up with, because I think I've said a lot here, and it's a little maybe a fuzzy what's on the test, what's not, or whatever. So I'm going to put you in breakout rooms so that kind of like yesterday, you can come back. Wait, is that one? Yeah, I'm going to put you in breakout rooms. Oh, I'm sorry. I'm going to put you in breakout rooms so you can study, frankly. Like, I want you to just, you can look at this if you want. If you feel like you're solid with the exam and stuff, you can keep looking at this and come up with questions. But basically, I'm going to put you in breakout rooms and say, go back to studying or whatever you're doing before and helping each other. And hopefully there'll be a couple more questions that I can answer by the, when I come back before the bell rings. But basically, take advantage of this time to study with each other, to figure out what you think is clear and what's not, to trade phone numbers, etc. And then I will try to answer questions, in the last 15 minutes or so. So I'm going to put you in breakout rooms. Are there any? I would answer like a quick, dying question now, but if it's actually no, I'm not. I'm going to put you in breakout rooms. I apologize. I want to move on. if I know how. If I know how. Yes, here we go. Okay. Okay. Please join your breakout room as soon as possible. Again, I'll bring us all back. I'll walk around like I did last time. And I'll bring us back around after everybody has. And I'll turn off my video. And, I will Okay. Hello. Hello. You can hear me? Yes. Yes. Can
Yes.
you hear me? Oh, maybe not. Oh, maybe you cannot. Wait. Oh, yes, you can. Okay. Thank you. Thank you. Okay. So we have like 10 minutes. I really don't want to keep you late the way I mean, I still want to answer more questions out of class and do more office hours and stuff, but right after class, I know I'm always putting people in a position because all that. So what I want to say, we have 10 minutes. I'll answer quick questions if I can. I may say that I can't. Um, but while we were in the breakout rooms, um, this is what I realized something about not only what Gabrielle said, which was helpful. What everybody said was helpful. I mean, but um, uh, I also realized that if I've been saying I was going to post this test at 5, but that would mean posting it not only, it would mean posting in the middle of lab. So that would actually be really disruptive to Woo, to tell you the truth. I really should have thought of that before. I really don't. Oh, wait, hold on a second. No, wait, sorry. Great question. Okay, sorry. Gabrielle, just, I meant to confirm. Gabrielle just also asked, and the answer is no. The answer is no, 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 which is a good thing. To Gabrielle's question, like the very last part of your practice exam, where I talk about a gravitational ring, I'm crossing that out. Definitely not on your exam. Don't worry about it. I mean, yeah, just don't worry about it. It's not on your exam. Oh, is my finger? Hold on, maybe, can you? Hold on, test. And well, okay, I think people are hearing me, right? I'm just getting a notification that says you can't, but I think you're hearing me. What I'm saying is it occurred to me, I can't even leave this up to you because it's just a bad move on my part. It's totally disruptive to Woo and to Lab for me to release this exam right in the middle of while you're sitting there trying to do different physics. Saying this again, knowing how much people hate a bunch of changes, and I know that, I beg your forgiveness. A part of this is me, part of this is my personality, but part of it is, doing things a new way for the first time, electronically and in the virus and all that. So I do apologize. What I'm going to say, I was going to release the exam at 5. That was the arrangement. I really think, all things considered, that's uncool. And any extra hour that it's giving anybody, it's sort of not giving anybody else. So that's not. So what I'm saying is I will release the exam the moment you're out of lab. I hope you can hear me. I believe you're done with lab at 6:30, essentially. I will release the exam then. I think I can even put a delay thing in the Google Classroom. So the moment you're all out of lab is when you'll get the exam. That is an hour and a half different from what I said yesterday. I hope that doesn't mess anybody up, but I'm just saying it because I don't think it's fair otherwise, and I think it's great. So at 6:30, you'll get the exam. It's due midnight on Friday. It will not include that last bit about gravitational rings. If it makes any reference to fluid drag, it'll be for extra credit. That doesn't mean I can't ask you about an exponential function somewhere. Like, you're taking derivatives of cosines and stuff. I certainly could say, is this exponential function a solution to harmonic oscillation? Like, I think you've been asked that a million times. I could do that, but I'm not going to get into the whole fluid drag thing unless it's for extra credit. So that said, and we're not going to teach any, yeah, I think that's it. And I know that someone asked me yesterday for more typewritten solutions instead of the handwritten ones. And it was a very fair question. And I often do try to give typewritten solutions, and some of your solutions are typed. I did not get a chance to finish that. I didn't give you any more last night. So I apologize for that. I mean, I think I will try for the next one, but I don't think that, I'm sort of hoping that still this whole exam situation is fair enough that I don't think any of us should lose sleep over that. So all that said, if there are quick questions about logistics or fairness or expectations or grades, I'll answer them now. But other than that, I'm happy to let you go early or like in a second. So any questions about what's going to happen? Or can you hear, you can hear me, right? Wait,
Yes.
wait. Matteo, you can hear me, right?
Yes, I can.
Wait, but could someone just confirm if you can hear me? If you can't hear me, that's not great.
Yes.
Oh, so it's I can't hear you. Okay, thank you for confirming. I see what's happening now is I totally cannot hear any of you. But Okay, you can hear me. That's good. I can't hear you, but I guess you have. So I'm looking at the chat. If you have a question, I'm looking at the chat because I can't hear you. Oh, how many questions will the exam? Okay, yes. Right. So you're not responsible for the 1D ring. A great, fair question from Gabrielle. Will the exam be? Definitely few. Well, this whole exam, the practice exam, technically was 4 questions with many parts each. I mean, it was many questions, but technically your practice exam was 4 big questions, each of which had multiple parts. Your actual exam is, I believe it's 3 parts, each of which has many. I mean, it's 3 big questions, many parts as there was in the practice, and the practice was 4, yours is 3. I mean, I think is the case. So it's shorter, but it's formatted very much like that practice exam. Again, all right, I'm looking at the chat. There you go. All right. You know, and obviously I want everybody to take it seriously, but you know, people, it's possible to do badly on the first exam, still do well in the course and all that. Like nothing is about to end irrevocably for anybody's life tonight. Or is a lot of them, or is it all of them? Right? Is it all of them? I'm just looking at the chat. Which practice? Oh, well, yeah. I mean, that's a fair question. Well, there's many private questions. And which the best thing I could say about how the real exam is going to very closely resemble the practice exam. Okay, honestly, if it weren't for the take-home thing, which I am in class that you were all taking, you'd be shocked. I basically changed some numbers in the practice, and maybe do a twist here and there on a couple of problems, but it would look very, very similar. I'm taking a little bit more variation here because otherwise it's a little bit of a waste of your time because you could like copy straight out. But as far as what I'm trying to say is you're an hour or so, will look very much like the practice, but a lot, and it will emphasize the same things. I can't say that it emphasizes the stuff in the practice basically equally, like taking 2 derivatives, the pendulum, the dot and cross products is basically the same distribution of material. The only thing is that in your practice exam, graphs and the charts and all the stories and stuff. I mean, honestly, in my heart, I think that what's going on in that problem is it's great. Like the actual questions are very educational, but that problem is so big and heavy on reading and graphs and charts that I can tell you that on your exam, you don't have to, that emphasis won't be there. Like whatever your exam, but you don't have to worry about your exam looking like that many graphs and that much reading. That's the best thing I can say about. But other than that, your exam is going to reflect fairly equally what you saw in the practice. Oh, now that's a great question. Sorry, and I think this is going to be the last one I'm going to answer now, because to be really honest, every time I say, part of what I mean is that there are questions that show you're on top of things in general. So someone just asked me privately, someone said, I know you're giving us a few days for the exam, but how long do you really think it would actually take to complete? That's a really, actually, I don't know if I've ever been asked that before exactly. Well, the answer is that technically this is a 2-hour. It was originally written more or less to be taken in the lab period. So I think if you were totally on your game and you had nothing else in your life and you had super studied and I usually do a bigger thing about this, but if you had actually gone through the practice exam like 3 times confidently, by the time you took it your 3rd time, you could do you did it faster than your 2nd time, then I would test conditions in my class. It's kind of like a 2-hour exam. If that helps you just get perspective on it. But again, yes, let me say, you're allowed to take as long as you want. You can go back and forth to it. But if you're trying to gauge yourself, or right, if you were sitting there and you're really struggling for 5 hours and looking things up and stuff, I mean, it probably shows you're not as on top of the material as you'd like. Yeah, it's like a 2-hour exam. That's a fair question. Oh, yeah, this is also a good question about grading and points. And yes, one thing, it's so funny, Walters is a great, I think, extremely fair and extremely transparent and extremely self-consistent grader. I love the way Walters grades. Some of the way he grades, like he learned directly from me, and some he did not, and I emulate him. And one thing is funny, I usually put the point values in the actual exam and the practice exam. I think I failed to do that in your practice exam. In your actual exam, I think it will say in each question how much points things are worth. In the exam itself, I won't break it down to a rubric. Like I'll say this part is worth 7 points maximum. And you should all know that that means you could get anywhere up to 7 points. And the only way you could get 0 points is if you literally wrote nothing down, or if you wrote down like, screw your mother, Yaverbaum. Like, you literally get points for every relevant and right thing you write. So, but say a question that says it's worth 7 points, that means the total you could get is 7, and you'll get anything up into there, blah, blah, blah. As to how I do the points, like if I'm saying like 3 points for recognizing the negative sign, 2 points for this, I will show you that rubric after I've graded and handed it back. You will see that clear rubric like Walter's is. I won't put that in the test itself because it becomes way too distracting and way too stressful and not helpful. But yes, I basically grade like Walter's, although he's better. And you'll see the breakdown of the grading like when you get back to the test. The other thing is you can argue grades with me. We'll get to that later. But if I grade your test and you find an error and you show me, then it's an error and I take it back. I can be more detailed when you, but believe me, I know that errors can be made and I'm not rigid about them. But yeah. Like 25% go to a diagram, stuff like that. I do like Walter's. I will not break that down in the original document, but I will when you get the grades back. Yeah. Like, so yeah. I think these questions also indicate that I can also tell from these questions, there's a lot when right before exams, when teachers say, are there any questions? A lot of times people will phrase things as questions, but they're really like thinly veiled panic attacks or like vitriol attacks at the teacher or the professor, right? Like I could say, are there any questions? And then someone could raise their hand and say like, yeah, do you think you might like not be an ass like you were last time on the test? I mean, that's ridiculous, of course, but like there's a way of asking a question which really basically says, we're all hating on everybody right now and we're all panicked and we're all going to do miserable and we think it's your fault. It doesn't seem like any of these questions indicate that. I think you guys are in good shape. I can tell by these questions that no one's freaking. It seems like people are not freaking out or blah, 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 or at a loss. And I think that's great. I really do. And I think people are going to do well. And again, it's possible not to. So if you do well, it does mean something. It's not a gift. But I think this is a strong class so far. So I will distribute this thing when your lab is over. You'll have till midnight, till Friday. You can talk to each other. I hope you do. I wish you all electron speed and the best of viral madness. So goodbye. Good luck. May the net force be with you. Oh, all right. I'm just now seeing this. Well, if Wu lets you out early, just as I was saying goodbye, I got this question. Wu might let you out early today, but I didn't know that. I can't. I don't know what to do with that information because I won't know it if he does. So I think we're just going to leave it that your lab, it comes out when your lab is over. Sorry. I mean, that's, if he happens to call, yeah, if someone wants to, okay, if someone texts me that your lab is over and you want, I could do that, but then it's going to freak out the other people. Let's just leave it that the thing is going, you're going to get the test when the lab is over. I'm sorry for so many changes, but I don't want to make any more changes now that people are hanging up. The exam will come out when your lab is over. You're a lovely group of people. You'll be here all week. Don't ever change. Keep on rocking in the free world. Peace in the Middle East. Don't play with scissors at the top of the stairs. Please wait a half hour after eating before going in the water. All of those were jokes. Good luck.